Bismillah ar-Rahman ar-Rahim. This video is about this representation for the exponential integral, the integral from positive t to infinity of e to the minus x over x. To be able to derive this representation, we will need first to study this integral from 0 to infinity of e to the minus t log t dt. This integral is related to the derivative of the gamma function, but here we will try to get its value without recourse to the gamma and the digamma functions. We need first to show that this integral is equal to minus gamma. Gamma is the Euler Mascheroni constant, and it is the limiting difference between the nth harmonic number and the natural logarithm of n. To evaluate this integral, we make use of the fact that e to the minus t is the limit as n tends to infinity of 1 minus t over n to the power n. We can replace e to the minus t by this limit here. The question now is whether we can interchange the order of limit and integration. So we will spend some time trying to justify taking the limit outside the integral. If we have the integral from 0 to n of log t times 1 minus t over n to the power n dt, rather than having n as a parameter in the integrand and also as the upper limit of integration, we can write down this integral from 0 to infinity, and then we introduce the indicator function t less than n. This is equal to 0 if t is greater than or equal to n and is equal to 1 if this condition is true, if t is strictly less than n. If there is a limit as n tends to infinity outside the integral, can we take the limit inside? Let's try to employ the dominated convergence theorem. If we have an integral of g of t and epsilon dt, epsilon is a parameter, t is the dummy variable of integration, and then here we have the limit as epsilon tends to a. Can we take this limit inside? The dominated convergence theorem provides a sufficient condition that makes swapping limit and integration valid. If we can upper bound the magnitude of the integrand by a function, and this function will be real valued and non-negative, that does not depend on the variable with respect to which we are taking the limit. So here we want the upper bound to be just a function of the dummy variable of integration. The upper bound should not depend on epsilon. If we can do this upper bounding, and the upper bound itself is integrable in the sense that if we carry out the integration we get a finite result, then yes, we can take the limit inside. Here is our integrand. As you can see, there is t, which is the dummy variable of integration, and then we have this n. We are interested in the limit as n tends to infinity. The first order of business is to upper bound the integrand by a function that depends only on t. To do this, we will make use of this inequality. For every positive x, log x is less than or equal to x minus 1. Proving this inequality is straightforward. We can just define the function x minus 1 minus log x. If we take the derivative with respect to x, we get 1 minus 1 over x. So the first derivative is equal to 0 when x is equal to 1. The first derivative is negative when x is between 0 and 1. And the first derivative is positive when x is greater than 1. The first derivative of this function is negative, then it's 0 at 1, then it is positive. This function has a local minimum at 1. So this function is greater than or equal to its value at 1. And at 1, this function is equal to 0. So this is greater than or equal to 0 with equality if and only if x is equal to 1. Let's use this inequality, replacing x by 1 minus small t over n, assuming that t is non-negative and is strictly less than n. So log 1 minus t over n is less than or equal to 1 minus t over n minus 1. That's minus t over n. Multiply both sides by the positive integer n. Exponentiate both sides. So we have e to the n log 1 minus t over n is less than or equal to e to the minus t. This left-hand side is just 1 minus t over n all to the power n. This is a proof that for t that is less than n, 1 minus t over n to the power n is upper bounded by e to the minus t. We have this inequality here. If t is greater than or equal to n, this indicator is 0, that indicator is 0. We have 0 less than or equal to 0, which is valid. And if t is less than n, then by this argument, we have that 1 minus t over n to the power n is less than or equal to e to the minus t. Thus, the magnitude of the integrand can be upper bounded by the magnitude of log t, and then the indicator function, and then e to the minus t. But the indicator function itself can be upper bounded by 1. We were able to upper bound the magnitude of the integrand by an upper bound that does not depend on n, the variable with respect to which we are interested in taking the limit. The upper bound depends only on the dummy variable of integration t. To be able to employ the dominated convergence theorem, we still have one more step, which is to show that the integral of the absolute value of log t times e to the minus t is finite when we integrate from 0 to infinity. Let's split the integral into an integral from 0 to 1 and another one from 1 to infinity. If t is greater than 1, then the absolute value of log t is equal to log t. If t is in the open interval from 0 to 1, the logarithm is negative, and so this absolute value is minus log t. For this log t, we can use the previous inequality that log t is less than or equal to t minus 1, which is less than or equal to t. And here we are integrating from 1 to infinity. We can upper bound by the integral from 0 to infinity, and this integral is equal to 1. Now for the other integral, e to the minus t is less than or equal to 1. We can upper bound e to the minus t by 1, And so this integral here is minus the integral from 0 to 1 of log t dt. We can do here integration by parts, and we also get 1. Since this integral is finite, we can apply the dominated convergence theorem. The limit as n tends to infinity of this integral, which is the same as that one, by the dominated convergence theorem, is equal to the integral of the limit of the integrand as n tends to infinity. We have n here and there. To evaluate this limit, note that t is held constant because we are taking the limit first, so t is a positive real number. As n gets larger and larger, this condition will eventually be true no matter how large t is. So the limit as n tends to infinity of this indicator is equal to 1. For this term here, the limit as n tends to infinity is e to the minus t. This is 1, this is e to the minus t. Now we have the integral of interest equal to the limit as n tends to infinity of this integral. Let's do the change of variables. T equal to nu. When t is equal to 0, u is equal to 0. When t is equal to n, u is equal to 1. Log t becomes log nu, which is log n plus log u. This t over n becomes u, and dt is equal to n du. We can split this into two integrals, one with log n and the other with log u. From here, we can take n log n, and the integration gives us minus 1 times 1 minus u to the power n plus 1 over n plus 1. When u is equal to 1, this is 0. When u is equal to 0, this is equal to 1 over n plus 1. So this integral is equal to n log n divided by n plus 1. For the other integral, let's do the substitution. Z equal to 1 minus u. When u is 0, z is 1. When u is 1, z is equal to 0. Du is equal to minus dz. So we can use this minus sign and make the integration from 0 to 1. This u becomes 1 minus z, and this 1 minus u becomes z. Let's do integration by parts. N integral from 0 to 1 log 1 minus z minus 1 over n plus 1 d 1 minus z to the power n plus 1. This gives us minus n over n plus 1, 1 minus z to the power n plus 1 log 1 minus z. And then we have plus n over n plus 1, the integral of 1 minus z to the power n plus 1 d log 1 minus z. So this will give us 1 over 1 minus z times minus 1. If we put z equal to 0, there is no problem. We have 1 minus 0, log 1 minus 0, log 1 is equal to 0. But if z approaches 1 from below, this guy goes to 0. Log 1 minus z tends to minus infinity. So what is the limit as z tends to 1 of log 1 minus z times 1 minus z to the power n plus 1, or we can divide by 1 minus z to the n plus 1 to the power minus 1. Again, the numerator tends to minus infinity as z tends to 1 from below. Now for the denominator, this guy goes to 0, and there is a minus 1 here, so this will go to infinity. To obtain the limit, we can apply L'Hopital's rule. This limit is equal to the limit of the ratio of the first derivatives. The first derivative of log 1 minus z is minus 1 over 1 minus z, and the first derivative of 1 minus z to the n plus 1 all to the minus 1 is minus the bracket to the power minus 2, and then we have minus n plus 1 times z to the power n. This tends to 1 as z tends to 1 without trouble. Now we need to obtain the limit as z tends to 1 of 1 minus z to the n plus 1 squared divided by 1 minus z. The numerator here can be written as 1 minus z to the power n plus 1 times 1 minus z to the power n plus 1 divided by 1 minus z. This ratio here is exactly the finite geometric series 1 plus z squared all the way to z to the power n. If we take the limit as z tends to 1, this summation here gives n plus 1, but then we have this bracket which makes the limit equal to 0. So this term here tends to 0 as z tends to 1 from below. The next step is to do this integration here. This is exactly the ratio that we have just handled when we studied the limit. 1 minus z to the n plus 1 over 1 minus z is 1 plus z squared all the way to z to the power n. This is a finite sum, and integrals are linear. We can simply integrate term by term. When we integrate 1 from 0 to 1, we get 1. When we integrate z, we get 1 half. When we integrate z squared, we get 1 over 3. And then the last term is 1 over n plus 1. So the integral from 0 to n of log t, 1 minus t over n to the power n dt, is given by n over n plus 1 times this difference, log n minus the harmonic number hn plus 1. We can subtract and add log n plus 1. Log n minus log n plus 1, that's log n over n plus 1. And then we have log n plus 1 minus the harmonic number hn plus 1. Now we can take the limit. This is 1. The logarithm is a continuous function. The argument tends to 1 as n tends to infinity. So the logarithm tends to 0 as n tends to infinity. We are left with the limit as n tends to infinity of the logarithm of n plus 1 minus hn plus 1. by definition, this is the negative of the Euler Mascheroni constant. This is minus gamma. This integral here is equal to minus gamma. Back to the main mission, we have the exponential integral from t to infinity of e to the minus x over x. T is positive. Let's split the integral into an integral from t to 1 and another from 1 to infinity. If t is in the open interval from 0 to 1, this integral is positive. If t is greater than 1, then this integral is equal to minus the integral from 1 to t e to the minus x over x dx. We will handle the integrals in a different way. For this one here, we do integration by parts. If x is equal to 1, log 1 is equal to 0. When x tends to infinity, e to the minus x tends to 0, log x tends to infinity. The limit is 0 as the denominator grows exponentially while the numerator grows logarithmically. Then we have minus integral from 1 to infinity log x, the derivative of this guy, e to the minus x dx times minus 1. So we get this guy here. This looks very much like the integral we have studied. The only difference is that this is from 1 to infinity, not from 0 to infinity. What about this one? Here we will subtract 1 and add 1. The integral of t to 1 of 1 over x dx is log x. At 1, this is 0. At t, this is log t. So this integral is minus log t. Now we need to deal with this part here. Integral from t to 1, e to the minus x minus 1 over x dx. We will write down this integral as an integral from 0 to 1 minus an integral from 0 to t. This one is done by parts. When x is equal to 1, the product of e to the minus x minus 1 times log x is 0. When x tends to 0 from the positive side, the logarithm tends to minus infinity, and this bracket tends to 0. We can write this product as log x divided by 1 over e to the minus x minus 1. We can multiply by minus e to the x over minus e to the x. This gives minus e to the minus x log x divided by 1 over e to the x minus 1. This minus sign goes with that minus sign, and we have here e to the minus x, which tends to 1 as x tends to 0. We are left with the limit of log x over 1 over e to the x minus 1. If x tends to 0 from the positive side, this tends to minus infinity, and this tends to plus infinity. If we apply L'Hopital's rule, the numerator becomes 1 over x, and the denominator becomes minus e to the x divided by the square of e to the x minus 1. As x tends to 0, the exponential goes to 1, and we are left with e to the x minus 1 squared divided by x. Both the numerator and denominator tend to 0 as x tends to 0. We can apply L'Hopital's rule again. The denominator becomes 1. The numerator is 2 e to the x times e to the x minus 1. As x tends to 0, this will be 0. Then we need to do minus the integral of 0 to 1 of log x. The derivative of this is e to the minus x times minus 1 dx. This is good. This is exactly the integral that we have studied earlier, but it is from 0 to 1. But this integral here, together with this one, will give us the integral of e to the minus x log x from 0 to infinity. And this is minus gamma. The Taylor series expansion of e to the minus x is 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial and so on. 1 goes away with this minus 1. Then we divide by x to obtain the series minus 1 plus x over 2 factorial minus x squared over 3 factorial and so on. The integrand can be written as the summation n from 1 to infinity of minus 1 to the power n x to the n minus 1 over the factorial of n. We can integrate this power series term by term. When we do this, we get t to the power n divided by n. So for positive t, in fact, for complex arguments of the non-positive real axis, e1 of t is minus gamma minus log t minus the summation n from 1 to infinity minus t to the power n divided by n times the factorial of n. If t approaches 0 from the positive side, the exponential integral tends to infinity due to this minus log t term. However, the limit as t tends to 0 of t, e1 of t, which is the limit as t tends to 0, t integral from t to infinity e to the minus x over x dx is equal to 0. The reason for this is that the limit as t tends to 0 plus of t log t is equal to 0, which can be verified using L'Hopital's rule.